So the goal for this next set of equations is to try to figure out a little bit about the velocity and acceleration of an object as it experiences a drag force. Now, one last thing that's worth understanding about the drag force is that when you throw something up in the air, and this is supposed to be our angry bird, that going up and going down are no longer symmetrical. Because on the way up, your drag force is opposing motion. That means it's in the same direction as gravity. On the way down, your drag force is opposing motion. That means it's in the opposite direction of gravity. So that's going to result in kind of an asymmetrical set of accelerations. So on your way up, you'll have an acceleration that eventually decreases to that of gravity. And in the case of on the way down, you start off with an acceleration of gravity that actually decreases to 0. And that's what I'd like to try to figure out. I'd like to try to figure out that if this is your acceleration time graph, what does your velocity time graph look like? So that's what we're going to derive here. It's worth talking about where the constant velocity equations come from and how you can get them using calculus. And that's what this picture is meant to show you. So if we start off with a constant acceleration graph, its equation can be described as A equals AO. And the calculus steps to deriving the velocity equation we know so well are as follows. The first thing we do is we replace the variable A with its calculus definition, which is the derivative of velocity. So dv dt essentially means the slope of a tangent line at every single time. That equals AO. The next thing we do is we separate the variables. So all I did was multiply both sides of this by dt. So I was left with dv equals a dt. And then the next thing I did was that I integrated. So I took the integral of both sides, I added up all the infinitesimally small changes in velocity, I added up all the infinitesimally small changes of acceleration with respect to time, and I basically tried to see what that integration was. So just to make things a little easier, I changed dv into v to the 0 dv. They mean the same thing. I changed a dt into a t0 dt. And then just applying our standard integration rules, it becomes pretty clear that v will go to v to the 1 divided by 1 plus 1. T will go to t to the 1 divided by 1 plus 1. So we're left with this equation. And then obviously we don't have to write t to the 1. So we end up with that equation. What are C1 and C2? They're constants. If you remember, as you take an integral, you have to add a constant in there because whatever your function is, if you take its derivative, any constant terms will go to 0. So taking the derivative loses information, therefore taking the integral we have to add it back in. We don't know what it is, it's some number like 4 or 12 or 17, so we'll just leave it as C. And we have two different ones, one for the velocity integration, one for the time integration. The next step is to combine our constants. Since they're just numbers, they have a sum and a subtraction and a product, and it's easiest just to combine them together. So I've said that C2 minus C1 is equal to some other number, C3. So I'm left with the equation V equals AT plus C3. So what's C3? You have to have some other information. So these are called initial conditions. And at our original time, we know that our velocity will be whatever our original velocity was. So to figure out what C3 is, I just take my equation, I plug in 0 for t and VO for v, and of course I see that VO is C3. And that's where I get my equation, v equals at plus vo. So those are the steps that you need to do to generate our simple velocity equation that we've used so much already. And basically, this kind of graph, this kind of acceleration, yields that kind of velocity time graph. Now the question is, if you have an acceleration that's decreasing to 0, what kind of graph does that yield? And that's what we're going to try to figure out. In order to answer the question, we're going to follow this exact same pattern. We're going to replace a with dv dt. We're going to separate variables and integrate. We're going to combine constants. And we're going to use our initial conditions to get rid of any other constants. It's a little bit tricky, and for the time of year that we're usually learning this, it's kind of a reach. And we will practice this many times before the spring when we need to use it. And you'll have this video to keep reviewing back on just to kind of get yourself used to these steps. So let's begin. So if you know my classroom at Manchester High School, this is the left side of a whiteboard. I'm going to go all the way across my front whiteboard, and then I'm going to go all the way across my side chalkboard. Derivation takes up a lot of space. We start with an equation that has an acceleration, and it just comes from our free body diagram or force picture. So sigma F equals ma. I list my forces, Fg minus Fd. I'm using downward as positive, equals ma. I plug in my equations, mg minus kv equals ma. So that's my acceleration equation that I'm going to start integrating to try to come up with a velocity function. So step 1, replace a with dv dt, just like we did before. And then we're going to separate variables. And the best I can do is multiply both sides by dt. So I have dt times that parentheses equals mdv. And that parentheses has a v in it, so I'm going to divide both sides by it so I get it over on the side that has the v. So I got all my terms with t on it over here, all my terms with v on it over here. So that's what we did before, it just ended up being a little bit more complicated. Now we have to integrate both sides. Now, this one here is going to be really easy to integrate. This one here is kind of complicated. We haven't seen this type of function where we have a velocity term on top and on the bottom. So we've got to figure out how to handle that. So I'll do what I did before. I've just added in a t to the 0 here since that's just 1, and that makes it really clear that the integral on this side is simple. It's just 1 over m times t plus whatever constant is there. We can't forget that there's missing information. Notice I've left this integral the same because it's tricky. And this is where we have to use a trick in calculus, which is that the way you do complicated integrals is you try to make them look like simple integrals that you know. Now, we know that the integral of dx over x equals the natural log of x plus a constant. Obviously, we don't know many integrals at all yet, but that's one of the very simple integrals that you'll be learning in calculus, and it's one of the ones given on the AP Physics equation sheet. So it's a great prototype integral, and if we can make our complicated one look like it, we can replace the unknown integral with just the natural log of some function. So how do we do that? There's a trick called U substitution. And in U substitution, you take a complex function that's got like a little mini function inside it, and you replace that mini function with just a letter. So we're going to say U is equal to mg minus kv. And that makes us have an integral that looks a lot more like dx over x. It's not perfect though. It's dv over u. We would really need something that would be du over u. So we're not quite there yet, but we're almost there. And what we need to do now is get rid of dv. So I did the integral on the left, just 1 over m times t plus c1. Now I want to go after this dv. So what I'm going to do is I'm going to write u in its full glory. U is actually a function of velocity. Instead of taking its time derivative, d dt, I'm going to take its velocity derivative, d dv. And you take that just like you took the time derivative. mg doesn't have a v in it, so it's a constant. Its derivative is 0. kv is kv to the first, so its derivative with respect to velocity is just minus k. So du dv is minus k. And rearranging that around, I'm just solving for dv, and I'm left with that it's minus du over k. Since dv is what I didn't want, I can sub that back in here. And now I'm left with a term that I can integrate. There's a minus here, there's a k there, but those are both constants, so they can pop out of the integral. And then other than that, I've got dx over x. I've got du over u. So I should, at this point, be able to take this integral. And that's what we're going to do. I probably combined too many steps here, but that integral of du over u multiplied by minus 1 over k, it just became ln u. Noticed we had our constant here, just some number that we don't know what it is, but it's a number. Then I immediately multiplied both sides by negative k to get ln u by itself. So the whole left side became minus k over mt minus kc1. Now I've got ln u all alone. And ln u I want to isolate because I want to get that velocity back in there. Velocity is what I was trying to get to begin with. And then of course I got minus kc2. So I'm going to combine my constants. I'm going to subtract kc1 or add kc1 over to both sides. Notice I put them in parentheses just to kind of show you what of this line here I'm going to be combining together. And I have combined everything in parentheses into this term minus ln c3. So that's weird, and it's not something you'd know to do on your own. But it is possible. I mean, don't forget c1 and c2 are just numbers. 4, 12, 17. K is just a number. So all we're saying is that there's these three numbers, c1, c2, and k, and that combined together, there's some other number whose minus natural log is them. And that's true for most numbers. Now the reason we wanted to do this is we want to get rid of this ln. We want to get the u by itself so we can start attacking it. And there's a trick with natural logs that lets us combine them. And I want you thinking about that as we go to the next shot. And hey, we're out of whiteboard space, so we actually had to wrap around to the board on the other side of the wall to keep going on this. It's a big derivation. And forgive yourself if you don't think you can ever do it by yourself at first. We'll have enough practice that you'll be able to. But as we're moving to the other board, think about why would another natural log be useful here? What is it about subtracting natural logs that's interesting? All right, so I've got what I had before. Minus k over m times t is natural log of u minus natural log of this random constant, ln c3. And you can see why the natural logs were useful now. I can combine them. So that whole right side just becomes the natural log of u over c3. And then I've got minus kt over m. So now I'm going to get rid of natural logs. You could be thinking about how you might go about doing that. I'm just going to e up both sides. So e'ing up the right means I have e to the minus kt over m, but e'ing up the right side means I've got e to the natural log, and that just cancels. So I'm just left with e to the minus kt over m equals u over c3. So I'm now done with natural logs, which makes me feel a lot better. Again, the goal was to get u by itself so I can sub v back in. So I'm going to multiply both sides by c3. So I have c3e to the minus kt over m equals u. And our next step is just going to be to put u, sub in u for the original definition of u so we can get velocity back into this equation. All right, almost done. So I've subbed u in. It was mg minus kv. And I solved for v. I added kv to both sides. I subtracted my exponential term over. And I ended up with v equals mg over k minus c3 over k e to the minus kt over m. And that's almost perfect. It's a velocity time equation. The only thing we don't know is what that constant c3 is, because we made it up. So again, that's the stuff you don't know unless somebody tells you initial conditions. Integrals introduce uncertainty, because when you take the derivative, you lose information, and underivating it doesn't give it back. You have to be told what initial conditions were. So our initial conditions are that we dropped this from rest, so the velocity was 0 at time t equals 0. So all I'm going to do is plug in 0 for velocity and 0 for time. That makes this e to the 0, which is just 1. So we end up with 0 equals mg over k minus c3 over k, telling us that c3 is mg. And then we're done. I plug in for c3, I plug in my mg. You can simplify it a little if you want, which I did. And this is the equation you're left with. So hopefully this graph makes sense at first. At the beginning, we have no velocity because we're dropping from rest. And this would be e to the 0, which would be 1. So 1 minus 1 is 0. So velocity is mg over k times 0, or very small. As time increases, t is going to go to infinity. So this will be e to the minus infinity, which is a very, very small number. So it'll basically be 1 minus 0. So we just end up with the velocity being mg over k. So it's kind of what we expect. Sharp increase in velocity at first. Not much change as time gets big. And we end up with a large acceleration at first and no acceleration at the end. But we always have a positive velocity because it is always continuing to go down. So that was a lot. And again, don't expect that you need to be able to do this all by yourself right now. We will do this many times before you're expected to do that. This is way before integration shows up in the year, usually, in calculus. And the only reason I do this at this time of the year is that I had students about 6 years ago tell me that waiting till the spring to talk about this kind of stuff is too late. You have to start it early on and hit it again and again and again. So to honor their advice, I try to do that. The big take-home message here is that v equals at plus vo, and even x equals 1/2 at squared plus vot plus xo, that comes from an acceleration function, the simplest one, a equals ao. You want to get the other two, you integrate that simple acceleration function. And that's how you get every other velocity function too. You take whatever the acceleration function is and integrate it. And this is an example that with practice you'll be able to do.